Wait for it. Wait for it. There we go. 2 hours UTC. Once again, we're here. Astronomy Daily Live. Hey everybody. Nice to see you. Hope everybody's doing well. Just getting all set up here like I do. Gonna get my I think I've got my chat already open. I do. I've got my chat already open. I'm going to reload my smartphone over here so I can see the live stream. There it is. There it is. So, hey, everybody, welcome. You can call me Cosmic, and welcome to another live stream where we gather a circle of friends and we talk astronomy for an hour or so. And I do this every single day. So if you're new to the channel, just coming in, make sure to subscribe, hit the notifications, and you can be reminded every single day when I go live. You can also, if you want to be part of the panel, little things will appear right down here. You can shoot me an email at cosmiclettuce@gmail.com. And when I go live, I will send you a link and you can be on the panel. That will be interesting. Haven't had that happen quite yet. So yeah, I hope everybody's doing well. Got some clouds here today, but pretty warm. Pretty warm. It's definitely spring in southeastern Arizona. So yeah, pretty typical spring so far. We can probably expect at least one more cold spell, maybe two, something like that. We've had snow on the 5th of May. So anything is still possible, but those kinds of things are sort of unlikely at this point. So yeah, I hope everybody's doing well, thinking astronomical things. There's a Chinese space station that is due to uh, plummet into the Earth's atmosphere in the next 24 to 48 hours or so. So, put on your hats, dive into your caves because it's coming for you. But yeah, I think if you live north or south of 43 degrees, I think that's the inclination of this satellite. uh, uh, you're safe. But if you're anywhere in between those two latitudes, then watch your head because it's coming down. It's coming down. Now, of course, statistically speaking, right? There's about a 70% chance that it's going to fall into the ocean. And most of it, of course, is going to burn up, before it actually gets to the ground. But it's a sizable chunk, so I would expect that pieces or a piece will definitely hit the ground. If it's uh, going to be going over land, then hopefully somebody will be able to see it and have the facilities to be able to record that event. But yeah, supposedly it's supposed to be happening in the next 24 to 48 hours. So yeah, get into your bunkers now because it's probably coming for you. So yeah, enjoy. That's it reminds me when when I was a kid, the thing was Skylab was coming down, sort of the same way. And I don't remember this Skylab crashed into the ocean. Don't remember exactly. Let's go find out, eh? Let's go find out. We can find that out probably pretty easily. Let me share my screen here. And so this isn't exactly astronomy talk, but it does have to do with space. So we can, since astronomy is the science of everything, then we can talk about Skylab, reentry. The day Skylab crashed to Earth. Well, let's just look at at the Wikipedia page on that, because that's there's actually a a Kickstarter campaign right now. I don't know if you've heard about it or not. They're trying to make a movie, and I believe it's called Searching for Skylab. So if you go on to Kickstarter, I think they're in their final few days of trying to raise funds to make that movie. Did an interview. Uh, the director of the movie did an interview on Tomorrow, TMRO, a few weeks ago, and um, yeah, I think a lot of the like the interviewing and all that is done. It's just production, production. So let's see. Skylab's demise in 1979 was an international media event with merchandising of t-shirts and hats with bullseyes. I remember the bullseyes. I had a friend who actually wore a um, uh, t-shirt, with a bullseye on it, and it was something like, oh, I forget what it said now. Something like Skylab Target or something like that. Let's see, a week before reentry, blah, 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 blah. NASA forecasted it would occur between July 10th and 14th, with the 12th being the most likely date. Royal Aircraft Establishment predicted the 14th. In the hours before the event, ground controllers adjusted Skylab's orientation to try to minimize the risk of reentry on a populated area. They aimed the station at a spot 810 miles southeast of Cape Town, South Africa. Reentry began at approximately 1637 UTC on the 11th of July. Air Force provided data. Station did not burn up as fast as NASA expected. Debris landed about 300 miles east of Perth and was found between, I'm not even going to try to pronounce those, residents and an airline pilot saw dozens of colorful fireworks-like flares as large pieces broke up in the atmosphere. They they find they find they find NASA for littering, which remained unpaid for 30 years. It was finally paid in April 2009. That's pretty funny. Um, so yeah, there's a piece of it that made it all the way through. So there's a little map. Reentry site and final orbits as predicted by NASA. So 34981. I guess this red zone was where it actually landed. Yeah. Airline, yeah. So yeah, it's sort of the same thing again with the Chinese space station. It's a big media event. Everybody's very very excited, and yeah, I guess in the next 24 to 48 hours it'll be down, and we can move on with more exciting things. But yeah, that was a pretty exciting event. We actually saw the election night, 1976. I was in Eastern Washington, and it was election night, so it was early November, 1976, and I remember. Yeah, I mean, I was just a kid, right? I was what, 7 or 8 at the time. Jimmy Carter was going to be um, um, elected president, and for some reason we were outside, and we saw most definitely some kind of a reentry of a satellite. It had broken up into a number of pieces, and there were sparks, and the whole thing. So yeah, I was lucky. I was lucky enough um, uh, to see that. So where is the center of the galaxy? Well, the center of the Milky Way galaxy is about 30,000 light years from us right now. Our sun and our solar system are um, um, orbiting the center of the galaxy. It takes about a quarter of a million years to go once around. So yeah, and the direction that it is towards the constellation of Sagittarius. So in the um, summer sky, summer fall sky, in the early evenings, if you look towards the constellation of Sagittarius, um, you will you will see it. And is the Earth flat? I don't know. I don't know. It certainly standing on Earth, it looks pretty flat, but there's some pretty good evidence that it's not. So if if you if you accept the idea that we humans have sent spacecraft out into space and have looked back on Earth, it looks pretty round, pretty spherical to me. All the other planets are spheres. Most of the moons are spheres. So it seems unlikely that the Earth wouldn't also be a sphere. So yeah, don't know though. That's actually one of the things I'm looking into. As a scientist, um, I I'm intensely curious about things, especially things that are like, huh, flat Earth. That's a little strange. um, Very, very skeptical, but also very, very open minded. So I've actually started looking into that a little bit. One of the regulars here, Tom, pointed me to sort of a starting point with this concept of zeticism, which is sort of an alternative scientific method, um, where you start with observations and develop theories based on that, as opposed to the regular scientific method, which you sort of make some guesses and then observations based on those guesses, and then correct your guesses. It's sort of a iterative kind of thing. So Is the Earth flat? I honestly, I personally don't know. Looks like there's pretty good evidence that it isn't, but definitely got to keep an open mind about those kinds of things. So thank you for the question, Jonathan. Appreciate that. Let's see what else. So yeah. So I'm not going to try to pronounce uh, um, uh, the um, the name of the satellite that is supposed to be coming down. Tianjin 1. I think there's a Tianjin 2 as well, and I believe that's still in orbit. I really wish I'm gonna flip back to the mug the mug here. Speaking of the mug, it is hydrogen hydroxide tonight, HOH tonight. A very calming, very awesome chemical that I greatly appreciate constantly. Cheers. So I really hope and wish really hard that all of humanity would get together and explore space together because uh, uh, it's such a big big place and it's ridiculous, I think, at least to sort of individually do things when we know that together there is a synergy, right? The um, uh, the combination of all the individuals um, is greater than just the sum of those parts, and so it would be so much better. It'd be so much funner, and I think that we would advance even further if we all worked um, together. But at this point, we're not. We don't want to endanger ourselves. Um, we don't want to give away our secrets, all of our plans, all of that. So China's going to do their thing. The United States is going to do their thing. Russia's going to do their thing. India's going to do their thing. On and on and on and on and on. And hopefully someday we'll realize that working together is so much better and so much easier, and we can accomplish so much more. Um, but yeah, until that day, I'm just rooting for everyone because yeah, I think you know I definitely think that going out into space is definitely uh, a great thing. I also think going down into the Earth might be an interesting thing as well. So yeah, I think we should be going both ways, both in and out, and let's just cover it all. I mean, we have the capabilities, we have the technology to do it, so let's do it. Let's do it. What you know? Uh, the only thing that's holding us back really is the will to do it. So and as I said, it seems to me that it'd be so much easier and so much more fun to, you know, do it all together. Because we're seeing, the Chinese sort, sort of do their Skylab now, and they're learning probably the same kinds of things that the United States learned back in the 70s, and it's like why can't we just move everybody ahead and whoever knows the most tells everybody else, and then we can all be caught up. We're all really really smart, so once we know a bunch of things, we can use that as a base and advance from there and get into the unknown. And but yeah, in the meantime, keep your heads low because it's coming down. It's coming down. So yeah, the next 24 to 48 hours, who knows? Who knows? Hopefully, hopefully, if it does impact land, it doesn't get into a populated area. Um, there's always a chance of that. But at the same time, if it gets around a populated area, there's more of a chance of seeing the reentry. So yeah, yeah, pretty exciting times though, for sure, for sure. All right, well, cool. Let's see. Cheers. I was watching uh, the SLOO live stream, SLOOH dot com. Now, SLOO is really, really awesome. They've got like I want to say five telescopes set up at the Canary Islands and one telescope down in Chile. And you can subscribe for as little as $5 a month. You can um, command these robotic telescopes to, you know, salute to a target and take pictures. And yeah, uh, I think for like $25 a month, it's pretty much unlimited, and so it's it's pretty cool. If you want to do things at that level. I think the largest telescope they have is a half meter, 20-inch. They've got some 14-inch scopes. I think they have a solar telescope too. It's some kind of a refractor, I think. So yeah, there's lots of opportunities, to sort of get your feet wet, um, at least take some pictures from some dark sites, and it's very very cool. Anyway, they did a live stream today, and one of the ladies on there was talking about how the moon orbits the Earth, and I wanted to jump on and say the moon is not orbiting the Earth, and maybe that's a surprise when you hear that, and it was a surprise to me when I realized this. I mean, it depends on your perspective, right? It depends on your perspective, but um, uh, in truth, in truth, the moon is actually in orbit, is being much more influenced by the sun than it is by the Earth. In fact, if you do the math, you will soon and quickly realize that the gravitational pull of the sun on the moon is twice as strong as the gravitational pull of the Earth on the moon. Now, I created a little graphic here. I did it on my Linux machine using LibreOffice. And LibreOffice is supposed to be able to, write out in Microsoft Word documents, .doc files. Okay, and so I had the formatting right. I wrote it all out. It looked really really nice. It was on a single page. It looked really really nice. When I transferred it over to this laptop, this one right here, um, and open it up as a Word doc, um, um, the formatting is like completely a little hard to read. But I'm going to show it to you anyway because I want you to see the numbers, and I want you to see that at least the gravitational pull of the sun on the moon is a little bit more than twice that of the gravitational pull of the Earth on the moon. And so what's actually happening, right, is that the Earth and moon share a common barycenter, and both objects are actually going around the sun. Um, but of course, the moon is, well, the moon and Earth, of course, are relatively close to one another. So what we get is sort of this weaving effect. So you can sort of imagine that the Earth is moving, along this elliptical orbit, and the moon is also moving in almost exactly the same orbit, except it's wobbling like that. And so relative to the Earth, if you're standing on the Earth, it looks like you the moon is going around us, but in fact, what it's doing is it's just sort of wobbling back and forth. So I'm going to show you this graphic with all the math. It's as I said, it's pretty ugly, but I'm going to show it to you anyway because so so be it, right? So as I said, this is sort of hard to read now, but this first equation up here is sort of the equation uh, to calculate the gravitational force on something in newtons. So it's the force equals the gravitational constant times m1 times m2 divided by r squared. R squared. So m1 is like the mass of the Earth or the mass of the sun. M2 is the mass of the moon. And then r is just the distance between either the sun and the moon or the Earth and the moon. And so I've just sort of laid out all the numbers here, and as science students will know, what you do in this case is you plug and chug. So you plug the numbers in, crank it around, and you get a result. So the gravitational constant is 6.67408 times 10 to the minus 11th meters cubed per kilogram per second squared. That's a very, very weird units there, but that's what it is. The mass of the Earth is 5.972 times 10 to the 24th kilograms. The mass of the moon is 7.347 times 10 to the 22 kilograms. So you can see that the Earth is about 100 times the mass of the moon. Okay, and then here's the mass of the sun. It's almost 2 times 10 to the 30th kilograms. So the sun is about 6 million times more massive than the Earth. And what is that? 600 million times the mass of the moon. Okay. So the distance between the Earth and the moon, that's this REM, is on average about 384,000 meters. And the distance between the moon and the sun is basically one astronomical unit, right? Which is the distance between the Earth and the sun, and that's 149 billion meters. So if you plug and chug, okay, if you put so if you put the mass of the moon in for M2 and the mass of the Earth in for M1, oh, let's do the sun first. Sorry. So the mass of the moon in M2, the mass of the sun in M1, and then R is just the distance between the sun and the moon. You get 4.36 times 10 to the 20th newtons. And if you do exactly the same thing for the Earth, you get about 2 times 10 to the 20th newtons. So the moon is feeling about twice as much gravitational pull from the sun as it does from the Earth. So pretty interesting. You would think that the Earth would have a larger gravitational influence on the moon, since we're sort of taught and told that the moon orbits the Earth. Well, it really doesn't. The Earth, of course, does affect the orbit of the moon as it goes around the sun, and vice versa as um, as well. But to say that the moon orbits the Earth like the Galilean moons orbit Jupiter, nope, not at all, not at all. So pretty interesting that that's actually one of the reasons why um, um, uh, the so-called orbital period of the moon going around the Earth is so slow. Don't know if you know this or not either, but Io, the innermost Galilean moon of Jupiter, is about as far away from Jupiter as our moon is from Earth. Okay, and Io takes about 16 hours to go around once. Okay, our moon uh, um, yeah. Um, Peer review. Yeah. I've got to have these numbers checked for sure. Um, uh, but the orbital um, period of our moon is about 29 days, right? 29 days uh, is about what? 696 hours as opposed to 16 hours. So that's almost 44 times longer at the same distance. So I would say now it's absolutely true, right? It's absolutely true that the sun is also playing a role in the orbit of Io and all of Jupiter's moons, of course. But in terms of the influence, and we could go through the same calculation there too, but in terms of influence, uh, the gravitational influence of the sun on, say, Io is much, much, much less. I can say that pretty definitively. Um, we could certainly, run the numbers, to find out. But yeah, when I first heard this, that the gravitational force exerted on the moon by the sun, was twice as much than the Earth, I was like, no, 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 no. Come on, isn't it obvious? Isn't it obvious that that can't be so? And then you run the numbers just like this, and it's like, huh, well, interesting. it changes your perspective. And the one thing that I am constantly in favor of is changing perspectives, trying to look at things from uh, many different ways. So of course, the Earth does affect the motion of the moon, but to say that the moon is in orbit around the Earth, I don't know. That I think that's a stretch. There, we just share sort of a common orbit and wobble around that common um, um, orbit around the sun. So yeah, pretty interesting to say the least. To say the least. All right, I'm trying to think what else we can look up here. I'm thinking let's look over to archive.org, see if there's anything interesting over there. Archive.org is the bleeding edge of not only physics and astrophysics and nuclear physics, but also mathematics, computer science, biology, finance, stats, electrical engineering, economics, all the latest, all the latest and greatest research in all of those areas are published here every weekday, uh, usually around 1 hour UTC, and then every weekday. So at the moment, it's the weekend now, so there aren't going to be any new ones, but we can look at last Friday's uh, papers and see if there's anything interesting. We sort of went through a little bit of this yesterday, but let's keep looking. Everybody's really excited about the galaxy that has no dark matter in it. So yeah, that'll keep them hopping for a while. Yeah, I sort of do too, Uncle Bill. I sort of see them uh, as a double planet, sharing a common orbit, going around the sun, and we're just sort of wobbling around. Sort of how I see it too. It is, it's a matter of perspective, and you know, one can also say that standing on the Earth, uh, the moon is for sure going around, right? Um, Nothing wrong with that. I I can completely accept that one too. Um, it's just from a different perspective that isn't really what's happening at all. So I think that's cool, and it's neat because both of those are right. It just depends on perspective. I like it. There doesn't always have to be you know one answer. There can be many answers. Algebra says that, right? Disk around Titari stars. I think we saw those. Yeah, there's the quasi periodic object that we were looking at before. If there's anything else interesting. Distance estimate of Tycho's supernova remnant. We present an approach to finding distances to young supernova remnants. Our method is based on hydrodynamic simulations uh, using this this code. That's cool. The explosion models, we have a classical blah 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 blah. Huh. So yeah, they throw it into a model right away and derive an estimate of the distance that way. That's pretty cool. Photometric analysis of the eclipsing polar MN Hydra. Why is it polar? I don't quite understand what polar means. As an eclipsing polar, is it polar or polar? I don't know. I don't know what a polar is. Why don't we find out? All these papers are great because they're an opportunity to learn new things, and I don't know what a polar is. So maybe usually how these papers go is that they have a little introduction where they sort of explain things. Yep, there's introduction. Okay, so polars are interacting binaries in which mass transfers from a dwarf secondary star to the primary, a magnetic white dwarf. So okay, huh? Interesting. So you've got a white dwarf sort of primary star and a secondary star that is some kind of like an M dwarf or something less massive than the white dwarf. The magnetic field is sufficiently high to prevent the formation of an accretion disk and channels the accretion stream at threading point and then guides the flow plunging into the white dwarf directly around the magnetic pole. Wow, that's pretty interesting. So, a type 1a supernova occurs when you have a white dwarf star orbiting a more massive primary star, and mass is falling onto the white dwarf until a sufficient amount of mass is sort of obtained uh, by the white dwarf in order to collapse its core, and then it explodes. But in this case, it's the white dwarf that is the primary star. Yeah, that's kind of interesting. Because of the variation of mass transfer rate, polars switch irregularly between high state and low state. In high state, polars present fast light intensity variation, which is known as flickering. The primary accretion pole below the orbital plane appears between phase 0.5 and 1, causes the intensity peak near phase 0.7, while the secondary accretion pole continues its emission all the way. Huh. And Hydra. Also, an eclipsing system. Photometric observations. Cool. So they give a revised ephemeris, which is just in the positions of both of the stars, I assume. Light curve low state presents one hump near phase 0.2, and those of high state showing obvious flickering. Cool. What was the period, did they say? 3.39 hours. So yeah, here's a dwarf star orbiting a white dwarf star every 3.39 hours. Wow. trucking. Wow. So again, this is old data. Um, 2009. From San Juan, Argentina. And then also over in Lucia. Okay, yeah. Most white dwarfs do have pretty strong magnetic fields anyway. Probably, likely, I guess, caused by their rotation. Because in order to have a magnetic field, you have to have some kind of electrical field. Those two go hand in hand. So you have to have uh, charged particles in motion in order to have a magnetic field. Yeah, okay, just the regular kind of photometric stuff. Here's all their data, all the light curves detected during 2009 to 2016. Hmm. Changing, highly variable. Quite a quite a difference in magnitude too. Do you see that? That's like, wow. That's a big change in magnitude. Something I could see my system very easily. 10-minute eclipse times the average of the eclipse ingress obtained. Blah 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 blah. Very cool. Photometric. Oh, okay, that's just the logs of the observations. Calculating mass loss. Kind of neat. Well, look at that. It's cut off there. I'm gonna have to fix that. More carefully and analysis the reasons for corresponding variation. So it looks like all their figures are at the end, which is always annoying. But there is your basic magnitude uh, equation. That's exactly the same one I'm using in my work, and it's always the same. Residuals, fits. Hmm. Yeah, they have to work on their formatting here a little bit. I don't think that's me. I think that's the paper itself. Work on that a little bit. Kind of hard to see the actual data. These dots are pretty big. Kind of hard to see what's a lot of the details in here. But again, pretty big changes in magnitude. Pretty cool. Flickering. Yeah, so they do Fourier transforms to see if there's any frequency stuff. And apparently in this data, which is a little bit easier to see, I guess this is what they'd be calling flickering. Um, Yeah, you can see that, maybe there's some periodic things there, but yeah, pretty not very much. So pretty random. Pretty random, I would say. That characterizes flickering for sure. Histogram of the variation timescales of all data. The dominating timescale is about 2 minutes. Pretty dynamic system, I have to say. Magnetosphere covers 42% of the surface area of the secondary. Can entangle. Yeah, I think that's cut off again. When matter flow reaches the threading point, uh, it'll be threaded by the magnetic field. Pretty cool. Optical observations of the eclipsing polar MN Hydra for 12 times enable us to get the following results. A revised ephemeris is given based on 10 more mid-eclipse times. Um, which cannot be explained in the angular momentum conservation case. Primary time scale of the flickering is about 2 minutes, which implies the threading point is about 30 radii above the surface of the white dwarf. White dwarfs typically are about the size of the Earth. At least that's my understanding. The state flickering stinks out. The frame of the two-pole model, the dominant accretion region is nearly face on to us at phase 0.7. Pretty cool, though. Pretty cool. White dwarfs are pretty amazing objects. Pretty amazing objects. Oh, that's kind of cool. That's pretty cool. I don't know if I've ever heard of a polar before. So yeah, definitely learned a little new tidbit there. That's kind of cool. Planet catalogs, cluster counts, calibration issue, or new physics. Oh, that's an interesting paper, The American Space Exploration Narrative from the Cold War through the Obama administration. That's pretty cool. All right, well, why don't we do a object of the day, and then we'll get out of here. Let's do a Messier object tonight. Also wanted to give a big shout out to cloudynights.com. Go and check them out. It's a very, very active forum, all things astronomical. Uh, Mainly amateurs, I would say, over there. Newbies and amateurs. Doesn't look like there's a lot of pros or anything over there, but very, very, very active group, and knowledgeable. Knows a lot of stuff. Um, Helpful, friendly. Um, yeah, seems to be a pretty nice group. There was a post the other day. Uh, I don't think I'll be able to find it now, but maybe I was following it. Let's see. Content I follow. It was about lazy astronomers. Uh, Where is that? Not that I follow. My content. Huh, I thought that was it. Yeah. All right. Well, I'm not going to take the time to find it now. Maybe I'll look for it and see if I can talk about it tomorrow or the next day or the next day, something like that. So let's look at a Messier object. So of course there's 110 Messier objects. So let's choose an integer between 1 and 110. Drum roll, please. Oh, M71. M71 is one of my favorites. This is a uh, now some people I think call this a very loose globular cluster. Some people are going to call it a very rich open cluster. I think that's M71. I think it's in the constellation of Sagitta, if I remember right. Let's go over to Simbad and find out a little bit more. Let's see what Simbad calls it. And maybe I'm completely wrong, but I don't think so. I think we didn't we search for this one before? We looked at this one already once, didn't we? Didn't we? Because it's coming up here again. Hmm. See how it's helping me? It's like it's remembering. It's remembering. So, you know what? Let's choose another one. Let's choose another one. Because yeah, I think we did M71. So let's do another one. Okay, ready? M82. Yeah, all right. M82 is a nice galaxy up there in Ursa Major. M82 is going to be, it's going to have a lot of info about it. It's one of those strange galaxies. Something amazing is happening at M82 for sure. Very active uh, active galaxy. Sure. So there's the right ascension, and there's the declination. As I said, it's up around Ursa Major, the Big Dipper. Um, pretty bright, pretty bright. You can, with a good pair of binoculars, you could probably see M82. It's right next to another galaxy, Messier object M81. Um, uh, so yeah, pretty easy to see in a telescope. This pair of galaxies, of course, is very awesome, very beautiful, sure. So let's see, bunch of different names. Wow, look at all the different names. Basically, just different catalogs. Yeah. So almost 5,000 papers that reference M82. It is a much studied galaxy for sure. So let's see. They've got distance measurements. Let's see how far away we think it is. Looks like the consensus is around maybe 4 or 5 million parsecs, megaparsecs, as they say. So a parsec is 3.26 light years. So 3.26 times 10 to the sixth is a megaparsec. And yeah, I don't know. Let's put it at around what about 4.5, is that sort of the average here? 4.5 times 4.5. So that puts it at almost 15 million light years away. So very, very close as far as galaxies go. Very, very close. But, going out, looking at this tonight, we're seeing it as it was 15 million years ago. So that light that is hitting your retina as you observe this left that galaxy 15 million years ago. So that's pretty cool to think about. It's like they've got the velocity um, pretty much nailed. Looks like maybe around 200 kilometers per second moving away from us. And let's see, anything else here? Still haven't figured out exactly what these things are. Observation logs. Observation logs. It's like some spectra over here, maybe. It's hard to tell. I'll have to dive into this at some point and understand this additional information a little bit better. There's quite a bit. As I said, M82 is one of those much studied objects. So let's see. Let's take a look at the picture over here. Very, very zoomed in, so we'll zoom out. Now, of course, this is not what it's going to look like through your telescope. This is a long exposure with a much larger telescope than what sort of normal people have access to. But it gives you an idea, sort of an edge-on type of thing, but it's got this stuff coming out this way, and it's got all this dark gas and dust around here. And I'm zooming out mainly because I want to see M81, which is right next door there. So there's M81. This guy. Whoop. There's M81, M82. Now, when you look at this pair through a telescope, what you're going to see is mainly just sort of the central area here in M81 and sort of, just this brighter disk area here. Seeing all this faint stuff out here, you're not really going to see that if you're just, looking through a telescope, with your naked eye. If you do a long exposure, with a camera and stuff, you can get closer to what these are. But yeah, very, very nice. A very, very nice pair. Spam away, Uncle Bill. Whoop. I'm zooming way out. Just sort of seeing if there's anything else interesting in the area. Doesn't look like it, but a very, very, very pretty pair of galaxies, to be sure. To be sure. All right, I think I'm going to call it an early evening tonight. I'm going to get out of here a little bit earlier than normal. Let's see, I've got to stop sharing. That's what I've got to do. Just like that. We're back over here. All right. Well, as I said, I think I'm going to get out of here for now. So yeah, we're going to do this again tomorrow night, same time, same place, 2 hours UTC. Let's talk astronomy again for another hour or more, right? All right, I'm going to get out of here. The doggies are calling. So, all right, I will see you tomorrow night. Take care. Peace. Cheers. Thumbs up. See you tomorrow night. Bye-bye.